Okay, good afternoon everyone. I welcome you back to my YouTube channel, and presenting before you this wonderful tutorial is Hamper Kliman. And if you are new to this channel, consider subscribing and also hitting the like button, and also don't forget to share. So today I come with another tutorial, and we shall be looking at the electric field. And of course, in my previous video I was teaching you how to do electric forces, Coulomb's forces, charging by induction and charging by conduction. And this time around we indulge into electric fields. Let's get started. Now, you might be wondering what an electric field is. For you to understand electric fields, suppose you have a sphere of this kind. You have a sphere, and this sphere is positively charged. Now, if you bring a small charge, and let's say this charge is positively charged, and we name this charge as charge 1. Charge 1 is going to feel an electric field from the sphere in this direction. Now notice that charge 1 is positively charged, so it will also feel a force of repulsion from the sphere in this direction. Charge 1 is a test charge. So because it is positively charged, and because this guy is positively charged, there is going to be that repulsion. To understand this concept very well, suppose we have different test charges. Let's name this test charge as test charge A. Alright, we name this test charge as test charge B. We can also name this test charge as, let me just call it C. If I get a sphere and place it here and make this sphere a negatively charged sphere, notice that A, let me just say this is positive, this test charge is also positive, and this test charge is positive. Notice that because A is positive and the sphere is negative, A is going to feel an electric field which will be attracting it due to this direction. If we were to have another sphere and we say that this sphere is positively charged, notice that B is positively charged, and our sphere is positively charged. So B is going to feel a force of repulsion due in this direction. And of course you can try out this one, and it's not different from what we have. You can try out this one, we see your understanding. It's not different from B, but then we can try it for practice sake. Now notice that the more A is getting closer to the sphere, the more the force of attraction. And the more air is distanced from the sphere, the less the force of attraction. In this case, the electric field, let me just use my other. Having established that concept, this means that an electric field is directly proportional to the force, and of course inversely proportional to the charge. Having established this concept, the electric field is equal to the force over the charge. So we particularly use this formula. But then let's try to do a little bit of some derivations of formulas. Let me just try to wrap my board. An electric field is equal to the force over the charge. Notice that the force is equal to Coulomb's constant, charge 1, charge 2 over the radius. This can also be written as the electric field is equal to, notice that we can replace what we have here, where there is F. We are going to have K, Q1, Q2 over R, all over by the charge 1, the charge. So from here, this charge and this charge can go. The electric field is going to equal to constant K, the charge, over by R2. And this is the formula that we'll be using for this particular topic. Now, it is also very important to note that the electric field is equal to the force over the charge. We can make force the subject, and if we make the force the subject, this is going to equal to the electric field times the charge. You can also take note of this formula. We shall be using it as well. Alright. So having established this, we can try to check out some practice questions. That is all you're just supposed to know about this topic. Alright, so we get to have this question here, and I'll try to simplify this question so that you get to understand. So they're saying that charge Q1 is equal to 7.00 microcoulomb, and it is at the origin. And charge 2 is equal to -5 microcoulomb and is on the x-axis, that is 0.3 meters from the origin. Find the magnitude and direction of the electric field at point P, which has coordinates 0.04 meters. Now, notice that charge 1 is positively charged. And from the diagram you have been given, charge 1 is exerting an electric field in this direction. Notice that charge P, upon feeling this electric field, moves in this direction. So we can deduce that P is positively charged. And also, when P acts on charge Q, it moves in this direction because there is a force of attraction, basically because Q2 is negatively charged. Notice that there is a force due upward, which is this force. Then there is a force of attraction that P is feeling towards Q2, and this force is in this direction. So between this force which is moving upward and this force which is moving in this direction, there is a vector sum E, which was simply calling as E1. For us to establish the magnitude and direction of the electric field at point P, we must be able to understand that from this angle and this angle that we have, this vector is simply theta equal to 90 degrees. That is very much simple to understand because it's very much it's intersecting between E1 and E2. So we have E1 here, we have E1 here, we have E2 here, then we have the total magnitude vector, which we are calling as E, here. So this is just vectors. If you understand how to use vectors, then you understand this question. Alright, let's now get started. So notice that the electric field is equal to K charge 1 over R squared. This can be written as, what is K? K is simply 8.99 multiplied by 10 to the power 9. So Q1 is 7 microcoulomb. So we're going to have our 7 microcoulomb there. So this will be 7 multiplied by 0 multiplied by 10 to the power negative, supposed to be negative 6 coulomb. So first of all, find the magnitude due to Q1 in this direction toward P. So that's the first thing to do. What is the distance? The distance is from Q1 to P, the distance is 0.4. So we're going to put our 0.4 like that, power 2. Let me just try to do my calculations. This is 8.99. Okay, so I already did my calculations already. Okay, so I'm getting something like 3.93 multiplied by 10 power 5. Now remember that this is supposed to be, these are electric fields, so remember that the electric field is equal to the force over the charge. Force is newtons, charge is coulomb, so this is Newton per coulomb. Of course we have newtons per coulomb. Now this is the total sum vector that we have. So, having calculated the total sum vector, we can now calculate the individual vectors. So for E1, remember that for E1 we only have one vector. E1 only has one vector, and the vector is in this direction in the y. We don't have any vector for E1 in the x, so in this case we only have E1 y. We don't have E1 x, so in this case it will be equal to 0 Newton per coulomb already. Okay, so let's proceed. So of course we are going to find our E1 y, and that is going to equal to 3.93 multiplied by 10 to the power, this is supposed to be power 5, multiplied by, this is supposed to be in the y, so in the y we use sine. Okay, sine, remember the angle. What is the angle? The angle is 90 degrees because of this perpendicular line here. Okay, the angle that we're using is 90 degrees. Remember there is a perpendicular line here in this direction. We have a line here in this direction, so we are using this angle. We are using this particular angle. Okay, so this is sine 90. So if we calculate that, E1y is going to equal to, this is going to be 3.93 multiplied by 10 to the power 5 Newton per coulomb. And this makes sense because sine of 90 is 1. Okay, so we can write this answer here. So we can say E1 y is equal to 3.93 multiplied by 10 to the power 5. Right. Then of course E1x, we already know it is 0.0 Newton per coulomb. Alright, let's try to do for Q2, because the question is saying we find the magnitude and direction of the electric field at point P. So point P is feeding electric fields from Q1 and Q2. We have calculated for Q1. Now we calculate for Q2. All right. We calculate for it for Q2, the electric field for Q2. So in this case, we can write our formula. The electric field is equal to K charge over R power 2. So our charge, our Coulomb's constant is 8.99 multiplied by 10 to the power 9. What is the charge for Q2? Q2, of course, is exerting a charge of -5 coulombs. So of course, because we're using absolute value, so it will just be 5.0 multiplied by 10 to the power -6. So the line that we are using, what is the distance? We are using 5. So that's 0.5. Like that. And of course, having done my calculations, you will find 1. This is supposed to be, let me try to redo my calculation. So this is 10 to the power 8.99 multiplied by 10 to the power 9. 5 multiplied by 10 to the power -6 divided by K. So I'm getting my answer to be 0. This is supposed to be 1.80 in standard form multiplied by 10 to the power 5 Newton per coulomb. All right. Okay. So if you want, you can write it as a whole number. If you want to write it as a whole number, 1.80 multiplied by 10 to the power 5 in one number is just 180,000 Newton per coulomb. But anyway, we leave it in standard form. Now, having done that, now notice that Q2 has a vector in this direction, which we can call E2y, and a vector in this direction, okay, which we can call E to, this is supposed to be E to X, E to Y is supposed to be E to X. So this is supposed to be E to X. Okay, so let's try to calculate E to X. All right, so E to X is going to equal to 1.80 multiplied by 10 to the power 5 in the x we have cosine. What angle are we going to use? Alright, so for e to x, when you check what we have here, notice that we want to find for q2. So if we want to find for q2, if we're using cosine is equal to adjacent over hypotenuse. So if this is what we have our curve, then it means that this is our hypotenuse and our adjacent is that number. So in this case, we are going to have cosine is going to equal to our adjacent is here, our hypotenuse remains this guy here, remains 0.5. So having noted that, this can also be written as cosine is equal to our adjacent is 0.3, our hypotenuse is 0.5, and this is going to be 0.6. So we can use that. So this would be 0.6. Therefore e to x is going to equal to, so if you do your multiplication in that manner, you will get 1.8 multiplied by 10 to the power 5. Newton per coulomb, like that. Let's try to do in e to y. So e to y is going to be that same number. This is 1.80 multiplied by 10 to the power 5. In the y it is sine. So notice that sine is opposite over hypotenuse. So sine this time around, it's going to, what is the opposite? Opposite is 0.4, hypotenuse is 0.5, and what do we get? 0.8. So this time around we'll be using 0.8. Okay, and remember that in the y, for the y it was going downward, the vector was going downward, this guy, it was moving in this direction, which is the negative direction. So you also consider that. So therefore e to y is going to equal to negative, that is if we do everything so the angle is negative, of course it will be negative 1.44 multiplied by 10 to the power 5 Newton per coulomb. So from here we can now sum everything. We can say that the electric field in the x is going to equal to, so in the x we have 1.8 multiplied by 10 to the power 5 plus, in the x we also have a 0.0 newtons, which happens to be here, and our final x will just be 1.8 multiplied by 10 to the power 5. We now do summation in the y. So in the y we have here 3.9, 3 multiplied by 10 to the power 5. Notice that this is negative, so it will be minus 1.4. Okay, so that would be minus 1.4 minus 1.4 4 multiplied by 10 to the power 5. You don't be column. So EY, if you do your calculations properly, you are supposed to get something like 2.9. Okay, then multiplied by 10 to the power 5 Newton per column. So it's very tricky, but all you have to do is to just understand the concept. So from here everything now becomes simple. It's the computing into vectors which is a little bit challenging. So now I've done for both e to x and e to y. Found the component vectors of vector p experiencing an electric field from Q1 and Q2. So after having done everything, you now have EX and EY. You can use them to find this vector component which we are looking for. The vector component we are looking for is this one. Okay, let me just try to clear this. The vector component that we're looking for is this one. So for you to find this one in summary, you will need first of all to calculate the electric field due to Q1 on P. So since P is positive, you have a vector component in this direction. That is why you only have E1Y for Q1. But for Q2, remember that this guy is feeling a force of attraction because this guy is negative. So, meaning there is going to be a vector component in this direction, which we are calling as E to X, then a vector component in this direction, which we are calling as E to Y. So you are calculating all these vectors because you want to know the vector component E. So to calculate that vector component E, we use the formula E is equal to the square root of EX power 2 plus EY power 2. So you get this, you can get this electric field and this electric field, you put them in there, whatever you calculate is the final answer. And of course, if you want to answer, okay, they're saying find the force on the charge. So if you want to calculate the force, remember that force is equal to, okay, let's say the electric field calculated here is B. So electric field is equal to force over the charge. So if you calculate, if you make force the subject, you find the electric field multiplied by the charge. So in this case, our electric field we've already calculated, it's B, and the charge has already been given to be 2 multiplied by 10 to the power 8. So 2.0 multiplied by 10 to the power negative 8. And whatever you are going to get, we can call it C in newtons. So this is just how you go about solving this question. and questions that are under electric fields. If this video has been helpful, consider subscribing. Thank you so much.